lecture on programming, data analysis, and deep learning in Python. There have been some questions because I'm doing a little bit of repetition of linear algebra. And I know this is quite boring for some of you and quite trivial. So the idea behind that is this, that there's people from different fields in this lecture, and not all of them had a lot of linear algebra during their studies. So we have to do some repetitions, and also for the others. So what I'm trying to do is to actually convey a little bit of intuition, and no proofs obviously, behind a lot of these linear algebra operations that we're doing. And I think it's important, even if you know linear algebra, because this is where your bugs will be. So if you do some deep learning, it's very important to have like a good intuition behind all the operations that you're doing, because a lot of your bugs will be somewhere in the matrix multiplications, right? There will be bugs that will be very difficult to find. So the plan is this, I try to keep it short, that I spend maybe, I don't know, maybe 10 to 15 minutes giving some more intuition on matrix multiplication, which might be relatively trivial for some of you. But then we go back to NumPy, and I show you how to access elements and how to deal with all of that in NumPy. And then towards the end of the lecture, there will be a little bit more basic stuff regarding systems of linear equations. But not much, and then we go back to NumPy. So there will be a little bit of math basics, but I think it's only this lecture and maybe the next one, and then we are done with that. I hope everybody is happy with that. So for whom of you is the math stuff that we are doing too trivial? Okay, for whom is it too difficult? Okay, and then there's a lot of people watching these lectures on video. Okay, so I try to give you a little bit of intuition behind matrix multiplication. So last week we multiplied some matrices. And so basically there's 5 different ways of looking at matrix multiplications, and some of them will become important when we go towards deep learning. So I think the basic stuff, the basic way that everybody starts to think about matrix multiplication is the following. Say you have 2 matrices, 1, 0, 1, 0, 1, 1, and 1, 2, 1, 1, 0, 2. Then the first thing that you should always do, and that you should probably also do in your code, is to check the dimensions. So it never hurts to put in some assertions in your code to check the dimensions, to make sure that all the dimensions of your matrices are what you expect them to do. So this is a 2 by 3 matrix, and this is 3 by 2. So the first thing that you need to check is whether these dimensions match. They do match, so you can multiply them, and the result will be 2 by 2. Okay, and now we have different ways of looking at this operation. And the first, most basic perspective is that each entry here is the dot product of one row of this matrix and one column of this matrix, right? This is, I think, the most basic one. So this entry here is the dot product of this row and this column. So it's 1 times 1 plus 1 times 1, that's 2. This entry here is this row times this column. So it's 1 times 1 plus 1 times 2, it's 3. This entry here is this row times this column. So it's 1 times 2 plus 1 times 1, it's 3. And this entry here is this row times this column. So it's 1 times 0 plus 1 times 0 plus 1 times 2, it's 2. So basically we take the rows of this matrix, we take the columns of this matrix, and the dot product gives us the entries in the result. So this is the first perspective. So it's rows dot columns, I would say. Rows dot columns. And this is nice, but so I think the second perspective is more important, especially for deep learning. And the second perspective looks at this matrix as a whole. So it's basically, so we have the same matrices, 0, 1, 1, 1, 2, 1, and 1, 0, 2. So in the second perspective, we look at this matrix A as a whole, and for this matrix, we look at the individual columns. And we think of applying this or multiplying this matrix with this column, which gives us the first column of the result, and then multiplying this matrix with the second column, which gives us the second column of the result. So A times the first column, or A dot the first column, it's the same, right? It's this column, 2, 3. And A times this column 1, 0, 2 gives us the second column, which is the column 3, 2. So here you view the matrix multiplication as a series of matrix vector multiplications. And it's like a batch operation. If you want to multiply this matrix with many vectors at one time, you just put all the vectors into the columns of this matrix, and then you multiply the two matrices. And the effect of that is to multiply this matrix with every column of the matrix B. So the perspective is multiplying this matrix with this column, gives us this column. For whom is this clear? Okay. So that's the second perspective. And this will be very important in deep learning when we want to multiply a matrix with a lot of vectors at a time. It will be very inefficient to do a for loop and multiply the matrix by the vector 1 at a time. And instead what we will do is we will horizontally stack all the vectors into a big matrix and just multiply the two matrices. And that will be much faster. So that's the second perspective. And I think this is the most, in my opinion, that's for us the most important perspective on matrix multiplication. So it's A dot every column of B. Then there's three more perspectives. One is very similar to this one, but now you multiply each row of A with the matrix B. So it's the same matrices 1, 1, 0, 1, 1, and 1, 2, 1, 1, 0, 2. And in this perspective, you multiply from the left, you multiply this row vector from the left with this matrix, which gives you the first row of the result. So multiplying this row from the left with this entire matrix gives us the first row of the result, which is the row vector 2, 3. And then we do the same with the second row. And obviously, the result is the same in all perspectives. In the second row, we multiply the second row as a row vector from the left with this matrix B. And this gives us the second row of the result, 3, 2. So the third perspective is rows of A dot B. And there are some implementations of neural networks where you do this, you multiply rows with a matrix. But I think we will mostly stick to this way of doing it. Then there's a fourth way where I think the place should be sufficient. I'll do it over here. So the fourth perspective is the columns of the first matrix times the rows of the second matrix. So we have these two matrices, 1, 0, 1, 0, 1, 1, and 1, 2, 1, and 1, 0, 2. And what we do in this matrix, in this way of viewing matrix multiplication, we multiply this column times this row, and this will give us a full 2 by 2 matrix, right? So this column times this row gives us a matrix 1, 0. So it's 1, 0 times 1, 1. And then, so this will then give us the matrix 1, 0, 1, 0. This is this part. But then we also have to take the other columns of A and the other rows. So the next step is to multiply the second column of A with the second row of B. So, and we add them. So this will be plus 0, 1 times 2, 0 plus the third column of A times the third row of B. 1, 1 times 1, 2. And then if we do this multiplication, so the first row will be 0, 0, and the second row will be 2 times 1, 2, 0. And this part will be 1, 2, 1, 2. And then we just add these three matrices. And this gives us 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. And 0 plus 0 plus 2 is 2. So all of these, you do the same calculations, right? It's just different ways of looking at these calculations. And then we have a fifth way, which I hope fits here. Okay, this is columns of A dot rows of B, then add columns of A dot rows of B, then add. And the fifth way is block multiplication. So actually we can also, from our matrices A and B, we can slice them into blocks. And if these blocks allow multiplication, then we can just multiply the blocks and the result will be correct. So let me take a different example. Say we have the matrix 1, 0, 1, 0, 0, 1, 0, 1, times 1, 1, 1, 1, 2, 2, 2, 2. Now if we look at this matrix, it's not immediately obvious what the result will be, right? But if you pay a bit close attention, then you see the identity matrix here and the identity matrix here. Identity matrix, maybe I have to explain. The identity matrix is a matrix that has ones on the diagonal and zeros on the off diagonal. And if you multiply this with any vector, this matrix times any vector is the same vector. Right. We call this identity. So we see the identity here and here, and we see a matrix of ones here and a matrix of twos here. So we can write this as identity matrix here and identity matrix next to it, and some matrix of ones here and a matrix of twos below that. And now we can do block multiplication. So the result will be this block times this block plus this block times this block. And I times a matrix of ones is just a matrix of ones. So this is I times this matrix of all ones plus I times the matrix of all twos. And this is just the matrix of all ones plus a matrix of all twos, which is a matrix of all threes. So the result will be 3, 3, 3, 3. And this block multiplication can often help if you want to make matrix multiplication faster. For example, you want to do some parallel computation of that on multiple cores or on the graphics card. Then you can speed up matrix multiplication by slicing the matrix into blocks. And the nice thing is if you can formally multiply the blocks, then the result will always be correct. So it's a nice way of making matrix multiplication faster. Okay, and then, of course, we have to be careful with matrices. We saw already last week that A times B is not B times A, right? So matrix multiplication is not commutative. So you have to be a bit careful when you're coding that. Are there any questions regarding these 4 kinds of 5 perspectives on matrix multiplication? Yes?
Where's the, in perspective 5, where did the I times 1, 2, where did the 1, 2 come from?
This, I times 1 plus I times 2? This? Oh, it's just by seeing that this is I, this part. Here, these 2 columns, they are the identity matrix. And these 2 columns, they are the identity matrix again. And this is what I called 1, a matrix of all ones. And this is what I called a matrix of all twos. So this is just short for 1, 1, 1, 1 here. And 2, 2, 2, 2 here. I mean, I just invented this notation, right? That was your question? That answers your question? Okay. Okay, so that was the repetition of intuition on matrix multiplication. And let's just quickly implement that in Python. So if we want to implement that in Python, we import numpy as np, as always. And for convenience, we from numpy import dot. Then let's code our 2 matrices, A and B. A as np dot array 101 is the first row, and the second row is 011. And B is np dot array, and the first row is 1, 2, 1, and the second row is 1, 0, 2, and the whole thing transposed. So A is this, B is this, and dot AB is this. And just to remind you, dot BA is something completely different, right? It's even not the same dimensions. Okay, so these are really 5 different perspectives on this one line of code, right? .ab. These are 5 different ways to view this line .ab. And depending on what you're implementing and what you're trying to do, one or the other perspective is preferable. So quite often, I think this is the preferred perspective on .ab. Multiplying some matrix A with a number of vectors that are horizontally stacked in B. Okay. Any questions so far? Okay. So let's look at different ways to create matrices. Yes. Yeah. This one?
Yes.
Yeah.
Why we didn't use the block multiplication in this case?
Which kind of blocks?
Like we did it in 5. Why we didn't use, maybe the first row is I, and the second one is I, the second one is 1 and 2.
Yeah, but this row is not I, right? I mean, this part is I.
Why we didn't use the block multiplication?
This is some kind of block multiplication where you slice it into this block and this block, I think. So I think in a way it is block multiplication. But you can slice the matrices in any kind of blocks that you want. And this was just to highlight that this is the thing that you would learn in most linear algebra lectures, right? So I think if you are introduced to matrix multiplication in linear algebra, most of the time you learn this perspective first. And not everybody learns all the other perspectives. This is just like intuitions, right? Okay, so if you want to create matrices, there's different ways to create matrices. And I think in the exercises you will need some random matrices. I think if you want to try something, it's sometimes nice to have a matrix with random entries. And also if you're doing deep learning, you will always start with matrices with random entries in the beginning, and then you will start refining these random entries. So there's different ways that you can get random entries. So let's get some matrix C. You can use np.random.rand. And what this gives you, it samples the entries individually from a uniform distribution between including 0 and excluding 1. So it's a uniform distribution. So 0 can be in there, but 1 cannot be in there. And it looks like this. So you just get random values between 0 and 1, basically. Then if you do that, then the data type will be float as a 64-bit in this case. You can also ask for the number of dimensions of an array, because these arrays, they can be general tensors, right? So they can have any number of dimensions. So C and is, you have 2 dimensions, right? The horizontal, vertical dimensions. And then we have this shape attribute, which gives you how many entries there are in the first dimension of the matrix, and how many. So this first number is how many rows are there, and the second number is how many columns are there. Then there's other random distributions. So you can sample from np random rand n, and n stands for normal distribution. So this is a Gaussian normal distribution. And then you give the dimensions. For example, you want 2 by 2 again. And this is normal distribution with mean 0 and variance 1. So it's a standard normal distribution. And then you can add some value to it to shift the mean, or you can multiply to change the variance. Oops, that should be a capital D. And so if you do a normal distribution, then obviously you can also get negative values. Yes?
What's mean?
The average. So if you sample like 1,000 values, then the average will be 0. And the variance of all the values will be 1. And it will be distributed. So the Gaussian distribution, if this is 0, and so it looks like this. So you get a lot of values here around 0, and then less and less values the further away you go from 0. So this is mu. It's a mean. It's a mean of all the values that you get. Yeah. Yes.
Can you use any type of distribution? I mean, for example, Pareto distribution. Is it always a new rand p, rand something? I don't know.
If you go to the documentation of NumPy, there's a huge number of distributions, and you can take any like pre-defined distributions, and then if you need more distributions that are not in NumPy, it might be that in SciPy. So there's a package that's Scientific Python. You can do import SciPy. There might be more distributions, I'm not sure. Then there's another package. There's a package that's called sklearn. It's for machine learning. It's the main package for machine learning. There might be more distributions in there. And then there's a statistics package where I forgot the name. Yeah, so you can just stretch it manually, right? So I think one thing that you can do is stretch it manually after you sample. So you sample first and then you modify it. I think in the random.rand there's a lot of parameters in there. So I think you can specify things like that. Yeah. Yeah. But if you go to the the main Python documentation on NumPy random, it's all there. Yes.
What is the difference between the D-type function and the normal type function?
So the D-type is specific for NumPy. So if you have a NumPy array, it's because NumPy is implemented inside very differently from the rest of Python. So inside NumPy, everything is C code and Fortran code. And these NumPy arrays, they are stored in your memory as like contiguous blocks of memory. They are not stored in like some Python style. It's just a block of memory where Python operates on. And Python has its own data types, which are completely different. NumPy has its own data types, which are completely different from the Python data types. And the order, how it's stored internally, can be C order or Fortran order, and so there's a lot of, in order to get the high performance that you get with a NumPy, it deviates a little bit from Python in that regard. Which has the benefit that if you already have some C code or some Fortran code which computes something, which happens for a lot of groups have some legacy Fortran code that somebody coded in the 70s that does some magic calculation, which is very inconvenient to use because it's Fortran. Then it's super easy to write a wrapper around that so that you can use this Fortran code from Python. And then you can do all your like the glue code, just to stitch together your program in Python, all the stuff that is not computationally intensive, and then the stuff where all the computations happens, that should be fast, that will be in Fortran or in C. I think that's the main benefit of NumPy. And actually, this is a lot of these NumPy and SciPy libraries inside. They are old libraries that existed before Python, which were coded in Fortran or C, and now just somebody wrote a wrapper, so now they can be used from Python. For example, this dot function. This dot function, it's not implemented in Python, right? So the dot function uses LAPACK, the linear algebra package, which I am pretty sure is implemented in Fortran. Does anybody know for LAPACK? It's implemented. There are different implementations, I think. I think it's implemented in Fortran. So when you say .ab, then the stuff is executed in Fortran super fast, and it's optimized for your machine and so on. Okay, that was a lot of long answer to your short question. But that's why you have your own data types in NumPy. Okay, so then there's, we all know the range function from Python. There's something similar in NumPy. It's called arange for array range. And it's basically the same as range. So it gives you, but it gives you an array and not a range object. And it starts at 0, excluding the number that you give it, and it's basically the same as range. It's just for arrays. Then quite often we want the identity matrix, so we have NP identity, maybe a 3 by 3 identity matrix. So it's just ones on the diagonal and zeros everywhere else. And sometimes we want a matrix of zeros. We can get that with np.zeros, maybe 2 by 3. And maybe we already want to fill the matrix with some values, some initial values, and you can use np.full. Maybe the shape should be 2 by 3, and it should be filled with 2.3 times e to the minus 4. So it just fills you the, gives you the filled, pre-filled matrix. Then if you want to access these elements, it's very similar to Python. Accessing elements. So maybe we have some matrix A, which is np random rand n, maybe 2 times 4, or maybe it's 4 times 5. So A looks like this. And then one of the things that you will do most in NumPy is accessing some of the elements of your matrix, right? So if you want to get the first row of A, you simply say A and then square brackets, and you just say which row it is. So you want the zeros row, which is, maybe I call it 0 row. Oops. So it just gives you the row at index 0. Now if you want to get the first element, or the element at position 0 from that row, you just do the same. You do 0 row at position 1, position 0, which gives you that value. It's just the value in the top left corner of A. And then you can put that together. So you can say that you can say A, and you want the zeros row, and from the zeros row you want the zeros column, and then you will just get that element directly. And because you will write this quite often, there's a slightly more convenient notation. So you can do this. So you just say which row you want, comma, which column you want. And you can also say that you want, you can do this. If you want the zeros column, but all the rows, you just do a colon, forgetting all the rows, and the zeros column. So this is now these zeros column here that you get. You can also do slicing as in Python. So you can take, for example, let's take the rows at position 1, excluding position 4, and the zeros column gives you this value, and this value. And the row 4 is not there, but it's excluded, right? So it gives you everything. I think you can also do this. Starting from column 1, including starting at row index 1, including all rows, column 0. It's the same. Yes?
But A1 to 4, 0 excluded actually only the 0th row, including the 4th row.
No, you start counting at 0. So this is row 0, 1, 2, 3.
That's what I mean, exactly. But you
So this will include...
the 5th row, which is not really what happened, right? Because it includes the last number.
Yeah, but the last number is row number 3.
I see, yeah.
Because you always start counting at 0, right? So this is row 0, this is row 1, this is row 2, and this is row 3.
Yeah.
And if I do this, I'm pretty sure that it should exclude this row. So it's like Python slicing. It always includes the first and excludes the last. I mean, it would be very confusing if it was different than the rest of Python. Okay, so we can also take some part of that. Maybe we want to take these middle 6 values here. So we take A starting at 1, row 1, excluding row 3. And starting at column 1, 2, 3, excluding column 4. Column 4. This gives us just the middle part of this matrix here. And then we can also assign to that. So you can set all these values to 1.2 e to the 3, or e to the 2. And now, so this. So you can, by this you can assign to some part of your matrix. If you paid attention here you have to be kind of careful. Because if you do, this is some part where NumPy is different from the rest of Python. If you remember, in Python, when we were slicing, when we were cutting some part out of a list or a list of lists, we always created a copy of that list, right? Does anybody have an idea why this is not the case in NumPy? So if we slice in Python, if we slice in NumPy, if we slice some part out of a matrix, NumPy will never do a copy of that matrix, yes?
So generally you work with very large matrices, and if you copy every time you slice, you do lots of slicing,
Yeah.
then you have lots of copies.
Yeah, so the answer is exactly correct. NumPy is optimized for people dealing with very big data sets, right? Imagine you do some experiment with a lot of measurements, and then you have, I don't know, a 1 gigabyte size matrix, and then you slice something out of that. And if NumPy would start copying that matrix every time you copy it, every time you slice, it would be a mess, right? So this is, I think, the most important difference that you have to take care of between Python and NumPy is that slicing in Python always creates a copy, and slicing in NumPy never creates a copy. The reason being performance, right? So if we go back, or maybe create a, let's create a new 5x5 matrix. B is NumPy random rand n 5 by 5. Okay, so this is our 5 by 5 matrix with normally distributed values. And now let's create different views on this matrix. So maybe we have view 1, or slice 1, which is B. So if we first do the rows starting 0, excluding row 3, columns starting at 0, excluding column 3. It's this view. And then we create a second view, which is B starting row 2, excluding row 5, and starting column 2, excluding column 5. And view 2 is this. And then we create a third view, which is B starting row 1, excluding column 3, and starting column 2, excluding column 4. Now view 1, view 2, and view 3, they look like they're different matrices, but you have to be careful that they are all views on the original matrix B. So they are all referring to the same underlying data, right? So now if you assign, so maybe at some point you open your data and then you slice it in different ways, you create different variables, and now you start writing into some of them. So maybe you want to now do some calculations, and in order to do these calculations, you will write in view 1. And you will say, or maybe you write in view 3, you will say that view 3, all the values, so all the rows and all the columns, should be 3. Now view 3 is this matrix. What else has changed? Can anybody say what else has changed? So we changed the matrix view 3, but what else did we change? Yes?
We probably also changed view 2 because the row 1, 2 excluding 3 means that also the row 2, 2 excluding 5 is affected.
Let's look at view 2. View 2 also got changed.
We probably also, we also changed view 1, and especially we changed B itself.
We also changed view 1, and we also changed B, right? So if you create a lot of views or a lot of slices on your matrix, as soon as you change one of them, you will change all of them, right? So you have to be a bit careful. So maybe let's say view 1. Now all the rows and all the columns we set to 1. And view 2, all the rows and all the columns we set to 2. And now if you look at B, so the first thing we did is changing view 3, this middle part, to 3, but then we overrode that by changing all these values to 1, and then we overrode that by changing all these values to 2. So by this you accumulate like changes in your matrix, yes?
Why are there sometimes dots in some entries of the matrix?
It's just to say why there's one dot.
Yeah.
I think it's to say it's a float. And it might also be that it's not exactly a 1.0, but it might be 1.0000, and there might be something else down there. I think this tells me two things. The first thing it tells me it's a float, and the second thing it tells me it might not be exactly 1. It might be approximately 1, up to the accuracy that Python actually prints at this thing. If it would be an integer, there would be no dot. So I think if we create a matrix C np dot full to 2 and fill it with 1. Now C doesn't have a dot behind the ones, and C dot D type is int 64. So it's 64-bit integers. Okay, so we have different views on our matrix. And now if we look at view 3 again, view 3 now looks like this, right? So view 3 got changed because we changed view 1, which overlapped in this part with view 3, and we changed view 2, which overlapped here with view 3. So by changing view 1 and view 2, we also changed view 3. Say you implemented an algorithm and you want to take the data, but then you want to do some calculations in that matrix. Does anybody have an idea of how you could do that? So say you wanted to prevent this effect that you overwrite the data when you're writing into your view. Yes?
Maybe explicitly create a copy of the initial matrix.
So the answer is we can try to explicitly create a copy of the matrix. So let's recreate a new random matrix. Maybe we can call it D. And now if we create a view on this matrix, view 1 will be this slice of the matrix. It's again this upper left slice. And we say dot copy. Then we create a copy of that matrix. So it looks exactly the same.
It should be D instead of.
Oh, sorry, yeah. Oh. Should be D. Okay. And now if we write into that, if we say view 1, all the rows and all the columns should be 1, then view 1 is this, and D is unchanged. But at the cost of having to make this copy, right? So the philosophy of NumPy is, if you want a copy, you have to tell it explicitly because it will be very slow if the matrix is large. Any questions on views and slices? Slices and copies. Okay, so then sometimes you want to select some parts of your matrix based on some criteria. So say you have some matrix with some values about some people. So you have some people with some names. So it's np.array. And the people are Bo, Fritz, Tim, Bo, Tim, Bo, and Bo. Maybe you played some card game and you have the results of that. Now you have an np.array of this strange thing here, the data type, U5, means that it's Unicode. So it's basically text. And now you play some card games, you get some results. So you have some data. np random rand n 7x4. Your data looks like this. And now what you can do is you can go back to your names array and say you want to have all the positions in your names array where the names are Bo. Oops. Sorry. So this gives you an array of truth values, of Boolean values, whether the name at that position was Bo or not. And quite often, if you want to get some subparts of some large matrices, you will use this. You will create a Boolean array of the same size as one of the dimensions of your array, and then you will select with that Boolean array. So what you can do now is maybe we call this ISPO, this array. And now we can select from our data, we can select all the rows where ISPO is true, right? So it will go through all the rows. So our data matrix is, let's maybe make sure that all the dimensions are correct. Data.shape. Data has 7 rows, and ISPO has 7 elements. So what we can do is we can use our ISPO array to index into the data array. And we do this by data, and I want to have all the rows where ISPO is true. And this gives me all the rows from my array where ISPO is true. And you can shorten this by saying data at the and I want to have the rows where names is bo. So what will happen here is your names equals bo will create your Boolean array where all the entries are true or false. And then you will use this Boolean array to index into the data array, into the rows, and select all the rows where the result of this thing is true. And you can combine this with other stuff. So, for example, you can also say data at all the rows where names is not bo, and from these just starting from the second column to the end. And this is something that you will see all the time in NumPy code, that somebody indexes into some matrix based on some criteria and maybe some indices. Yes?
Could you explain again? I didn't get it. How you or what do you do? I don't get it.
Okay, so here we create a matrix or a vector where each entry of the vector is a string. This has a length 7, as we see here. And then we have this data matrix, which has 7 rows and 4 columns. And if we say ISPO will be an array that will be created by these questions. Names equals bo operates on the whole array, on the whole array names at the same time. So this is something that you will see in Python over and over, that you don't have to do for loops to iterate over all the elements, but you do operations with the entire vector. So you put in the entire vector names, and for each element in that vector, you check whether the string at that position equals the string bo. And then it gives you back a vector now of Boolean values. And the Boolean values are true, false, false, true, and so on, right? And now you can use this Boolean vector. This has length 7 still. You can use it to pick rows out of data. And here you say data at the position, and now here you don't say position 7 or so, but you say, you give this a slice operator, you give it a Boolean vector of the appropriate size, and automatically this will pick all the rows from data where this array that you give it is true. And it will drop all the rows where this array is false. So it will take the first row, not the second row, not the third row, it will take the fourth row, not the next row, and it will take the 2 last rows. And then this is just a shortcut. It's just doing all these steps in one line of code. So this will, here this names equal bo, it will run this equals operator on the entire array, create this Boolean array, and then immediately in the same line of code, feed that into this slicing operator and select the rows from data where the resulting array is true. That's why I did it for you in like 5 lines of code, just to make clarify a little bit what this line of. So in practice, what everybody uses is just this line of code. But what actually happens is all the individual steps that I showed before. Yes. There was another question. Yes. How does Python know whether why we want that we want to select the rows? The true values. Okay, so if Python knows that we want the rows because we only have one brackets, right? The first pair of brackets always refers to the rows, and it's hard coded in Python that if the slice or in NumPy, if the slice operator gets a Boolean array of the appropriate size, and the Boolean array can only have true and false, then it will always give you the rows or columns or whatever you have at that position with the true values. So just, if you want the false values, then you have to negate that. You have to say names not equal bow. This gives you an array where the true values are the ones where in the other array they are the false values. Okay, this takes a little bit of practice, I think. But I think if you practice a little bit, it's not so difficult to do. Any more questions regarding slicing? Yes?
The shape of the names and the data must be identical, or?
Yeah, so if you index into data, then you can either index into the columns or the rows, right? So you can also say that from data, we want to have all the rows where ISBO and all the columns, right? This works. But if we say that data, we want to have all the columns and all the rows where ISBO is true, then this will not work, right? So what it will give you is index error. Boolean index did not match index array along dimension 1. Dimension is 4, but the corresponding Boolean dimension is 7. What this means, Python is complaining that ISBO is 7 elements long, but we only have 4 columns in data. So the Boolean array has to obviously to have the same length as the dimension of the matrix that we are slicing in. If it's too short, it doesn't work either. So it has to have exactly the same length as that dimension that we're slicing. And it wouldn't make sense if it would work. I think it's good for that Python crashes if the dimensions don't match, because otherwise we would get a bug that would be very difficult to fix, right? I mean, you can always, like, if you want to have it shorter, you can always slice some part of it before and then use it to index into that array. But you have to do it explicitly. Let's look at data. So you can also, something that you will also see very often is something that like this, data smaller 0. This gives you all the indices where data is negative. So for example, down here, data should be negative. It's negative 0.98. And now, for example, you want to have, you want to set all the negative values to 0. You can say data at the position data is smaller than 0 is 0. So what this did is created this big matrix with true and false values, which had exactly the same size as data. Then we use that to index into data, and we set all these values to 0. Or maybe we want data at the position, at the rows where names equals bo, we want to set it to numpy dot not a number. Oops, maybe Bo cheated in the card game, and now we want to set all his values to not a number. Okay, are there any questions so far? Now we go back to a little bit more of explanations on systems of linear equations, because you will need that for the exercise sheet, and you will probably do that a lot. So who of you has ever solved a system of linear equations? Not everybody. Good. Don't worry, I will do a 2x2 one, so it will not take too long. And it's very convenient to do in Python. Okay, so yes.
We have like one more question to the matrices there.
Yes.
If possible. So if I would want to kind of change all the columns depending on both, how would I do that?
The columns don't depend on both. So we have 4 columns, but we have 7 names. So we never. But we can do that. So let's do maybe for some reason suddenly or maybe the columns are something else. Maybe the columns are, I don't know. Maybe the columns are pets or something. So say we have dog, cat, dog. Chicken. Now our pets are this array. And now we can say data, I want to have all rows, and I want to have all the columns where pets is dog. Oops. This didn't work. Does anybody see the problem? So pets equals dog is false. Pets is this. Oh, it's a sorry. Pets is a list, right? That was stupid. Pets should be an np dot array. If you work in NumPy, you should index with NumPy arrays and not with lists, obviously. So now pets equals dog is this Boolean array, and now you can say data, I want to have all the rows and the columns where the pet is dog. That was your question, I think. Yeah. Okay. Any more questions on slicing? Okay, one of the most important application areas of matrices are systems of linear equations. Say we have 2 linear equations. We have 2x1 minus x2 is 0, and we have minus x1 plus 2x2 is 3. And these two equations are coupled, so I want to find x1 and x2 so that both equations are fulfilled at the same time. Then I can easily put that into a matrix. If I take all the coefficients, which are 2 here, -1 here, -1 here, and 2 here, and I write them as a matrix, I say 2, -1, -1, 2. I put this into a matrix, and then I put x1 and x2 into a vector, and I also put 0, 3 into a vector. Then I put this system of equations into this AX equals B. And if you, just by this matrix multiplication, you can easily see that it's the same. What this actually means, it's 2 times x1 minus 1 times x2 is 0, which is exactly the same row here, this equation here. And minus x1 plus 2 times x2 is 3, which is exactly this equation here. So this thing and this thing, they're just different ways to write exactly the same. It's exactly the same thing. And now what this actually means is, if we look at this, this specifies a line, and this specifies a line, and x1 and x2 are the positions where the two lines cross. So if we look at the rows, of this equation, then we have x1 here and x2 here. And let's look at the first row, at this equation, and let's look what happens if x2 is 0, then x1 should also be 0, right? If x2 is 0, in order for this equation to be fulfilled, x1 has also to be 0. So this will go through 0, 0. And as another point, if x1 is 1, then x2 should be 2, right? 2 times 1 minus 2 is also 0. So if x1 is 2, x1 is 1, then x2 should be 2. So now these both points fulfill the first equation, right? And I can easily get all the points that fulfill the first equations because they will all lie on this line that goes through these 2 points, because it's a linear equation. And then if we look at the second equation, let's look at which points x1, x2 fulfill the second equation. And maybe first we can set x2 to 0, and if x2 is 0, then x1 should be -3. So if x2 is 0, so I'm here, then x1 should be -3. 1, 2, 3. It's -3. So the second line has to go through this point. And then if x1 is -1, then x2 should be 1, right? -1 times -1 is 1, plus 2 is 3. So if x1 is -1, x1 is -1, then x2 should be 1. Okay, and so all points that fulfill the second equation, they will lie on a line through these 2 points, which is this line. Yes, and so this is the first equation, and this is the second equation. And the only point that fulfills both the first and the second equation is the point where these 2 lines cross, which is this point. And there's a second way to look at the same system of equations. And this is by columns. So this is looking at the rows of the matrix. And the second one is looking at the columns of the matrix. And in the last lecture, we saw that multiplying this matrix times this vector actually tells you, x1 tells you how much you want of the first column of A, and x2 tells you how much you want of the second column of A. So let's put the first column. The first column is the first column is 2 to the right and 1 down. So this is the first column, where this was the first row and this was the second row. And the second column is 1 to the left, 1 to the left, and 2 up. So this is the second column. And now what this equation asks us is how much do we want of the first column and how much do we want of the second column to give us this point, 0, 3. So we actually want this point 0, 1, 2, 3. We want to get to this point. And this equation asks us how much do we want of this vector and how much do we want of that vector, so we get exactly at this point. And I think we can look at the solution here. So we will want 1 times the first vector and 2 times the second vector to get us here. So we take 1 times this vector plus 1 times this vector, which get us 1 to the left and 2 up. And then 1 more of this vector, which goes 1 more to the left and 2 more up, which goes exactly to this point. And this is just 2 different ways of looking at systems of linear equations. One is by rows, looking where lines meet, or in higher dimensions where hyperplanes meet. And the second is by columns, which I think it's more interesting. How much do we want of this vector and how much do we want of that vector in order to get to that point? For whom is this clear? Any questions? Okay. It's just it's again 2 different perspectives of looking at the same thing, right? Now, the question is AX equals B always solvable? And we can look at it in terms of rows, or in the row picture, or in terms of the column picture. Can anybody tell us, is AX equals B always solvable? Who thinks AX equals B is always solvable? Who thinks it's not always solvable? Okay, can anybody give me a reason in the row picture what could happen with these 2 lines so that AX equals B is not solvable? Yes? Yeah, if the lines are parallel, then there's no point where the lines cross, right? So there's no point that fulfills both, that lies on both lines. So say we have a system of equations. It's 2, 1, 2, 1 times x1, x2 equals 1, 2. And this would lead to parallel lines, and these lines don't cross. So it's not, there's no solution. And in the column picture, what happens in the column picture if the system is not solvable? Yes? Yeah. So how could it happen that by combining this vector and that vector, you cannot reach all the points in the, what has to be true about these two vectors so that by combining them, you cannot reach all the points in the plane. Yes? Yeah, or they have to be, exactly. They have to point into the same direction, right? Or they have to be linearly dependent. So if the first column is this, and the second column is a multiple of the same vector, then by adding any multiple of this vector and adding any multiple of that vector, we can only reach lines on points on this line. But we cannot reach, for example, if we have a B that's here, say our B is here, then by combining these two columns, we cannot reach this. And this happens if two of the rows, if one of the rows is a combination of the other rows, if one of the columns is a combination of the other columns, or if one of the rows is a combination of the other rows. So here the first row is 2 times the second row. So that gives us an indication that this is not solvable, and the first column and the second column are the same. Or the second column is 1 times the first column, so this also tells us that it's not solvable. Okay, if we want to solve a system, if it's solvable, there's this nice algorithm by Gauss. So say we have, let's take a solvable system of equations, a very simple one. Let's say 1, 1, 1, 2 times x1, x2 is 2, 3. So this is ax equals b. And it corresponds to the equations x1 plus x2 is 2, and x1 plus 2x2 is 3. And now we want to find x1 and x2 such that this is true. What we do is we do this, we tack on this vector to this matrix, which is what we call the augmented matrix. This is just a bit more convenient for writing. So we write this here. And now, if we subtract or add any multiple of any row to some other row, the solutions will be unchanged. The solutions stay the same if we add or subtract any multiple of any row to another row. So one thing that we can, sorry, that should be a 2 here. One thing that we can do is we can subtract the first row from the second row. So which will give us 1, 1, 2, 0, 1, 1. And now, if you think about, if you have a 0 here, so if you get this kind of staircase here, which we call a row echelon form in English. So if you get this kind of staircase form, then it's very easy to see the solution, because what this tells us is that 0 times x1 plus 1 times x2 is 1. Well, that's trivial. x2 is 1. And now we can back substitute that. Now we can go back here, and this one tells us that 1 times x1 plus 1 times x2, but we already know that x2 has to be 1, is 2. So x1 is also 1. And this is actually the algorithm that's also implemented in Python. And it's not implemented in Python, it's implemented in a software that's called LAPACK. And NumPy uses LAPACK to do these kinds of calculations. Okay, so if we want to do that in Python, it's actually very easy. Let's do our A. Systems of linear equations. Say A is np.array 1, 1. The first row is 1, 1. The second row is 1, 2. Okay, that's A. And B was np.array 2, 3. Oh, one brackets are missing. Transpose. So let's look at A. A is this, B is this. It's column vector. Then we can simply say numpy.linalg for linear algebra solve. And that's it. A comma B. And it gives us the solution 1, 1. And maybe we can go back to this example over here. So say A is np.array. What was this example was 2, -1, and -1, 2. And B was np.array 0, 3, 0, 3, transpose. Then we can say np linalg solve AB. And it gives us the solution that we see here. 1 to the right, 2 up. Okay. Any questions regarding systems of linear equations? Okay. Then sometimes we use NumPy for doing linear algebra and computing dot products and solving systems of equations. But sometimes we simply use NumPy to do a lot of calculations very fast. And the tool for doing that is universal functions. Ufuncs. And these are fast element-wise functions. So now you don't really look at your matrix as a matrix, you just look at your matrix as a bunch of numbers, and you want to execute some function on each of these numbers as fast as you can. So let's say we have a vector v, which is np random, normally distributed, maybe, I don't know. Let's start with 5 elements. But imagine that you have, I don't know, 50,000 elements or so with some data from your measurement. Then you can simply calculate the absolute. So let's look at v. And maybe you want the absolute value of that. And you can simply say np.abs v. And this is super fast, right? Whenever so as a general rule, if you're writing something in NumPy, and you find that you're yourself writing a for loop, you should think twice. Because there's a very high probability that as soon as you find yourself writing a for loop or a while loop, you're not doing it correctly. So instead of writing for loops, you should never step over all the individual elements in a vector or in a matrix, because that is super slow. And if instead you can run one function on the entire matrix at a time, it can be maybe 100 times faster. Right? So it's really much, much faster if you do if you skip. So when you write something in the first draft, you might want to do it with for loops. But if you can get rid of all the for loops, your code will run much faster afterwards. Or maybe you want to compute the square root of all the values, np square root of v. And here's a square root of a negative number, which gives you not a number. Or maybe you want to calculate the exponential of the matrix as np.exp of v, as e to the power of each element. Or maybe the logarithm base 2, let's say, log 2 of v. the logarithm base 2 of each of the numbers of the array. Or maybe the sign, np.sign of v. Or maybe you have a second matrix, maybe W, of the same length, np random, rand and 5. And you want to add them, you simply say v plus w, or v minus w. And this is the same as saying np.add vw. So the plus operator is actually overloaded by NumPy, so you don't have to say np.add, but you can just say plus, and it immediately works on the entire array. There's also np.maximum vw, which gives you obviously the maximum of both vectors. Or maybe you want to calculate the mean of v, np.mean of v. This is much faster than doing a for loop over all the elements, adding up all the elements and dividing by the number of elements. Maybe you have a new vector which is a range, maybe a range of 5 elements, and maybe you want to calculate the cumulative sum, which will be x cumulative sum. X was this. X is this, and the cumulative sum is just at each element adds all the previous elements. Or maybe the standard deviation. Maybe v, standard deviation. You can also say v.sort, which sorts v. So now all the elements in v are sorted. Okay. So in general, try to do, if you're working on a lot of data, try always to calculate with the entire matrices at a time, and try to avoid any for loops. There's also a number of tricks that I wanted to show you. One trick is the following. So say you have a vector x, which is np a range 10. So now x is this. So it's a 10-element vector, and say you want to reshape this. So instead of having one super long vector, you want to have half of it in the first row and half of it in the second row of a new matrix. And this is often convenient to create to change the shape of matrices. We have this command x.reshape, and in reshape you give it first the number of rows, which will be 2, and now you can either calculate the number of columns, which will be 5, or you can ask Python to calculate the number of columns for you by saying -1. And this reshapes the vector into this 2 cross 5 matrix. Maybe let's call this A. And maybe let's do that again with B is, maybe first we create a new vector Y, which is, there's a function np.repeat. Repeat the 1 10 times. It's just 1 10 times. And then you can say y.b equals y.reshape. 2 rows, calculate the number of columns for me. And now, say you want to stack A and B on top of each other. So the top half of the matrix should be A, and the bottom half of the matrix should be B. So you want a new matrix, which looks like this, A, B. The command simply looks like this. It calls np.vstack A, B. Oops, sorry, that didn't work. You have to give it a list. So this simply stacks the two matrices on top of each other. And there's also np.hstack, which is horizontally stack, A, B, which stacks them horizontally. Okay, with this, I think we're done for today, and have fun with the exercises, and see you next week. Thank you.